Hello, in this video we're going to give an introduction to parametric equations. A pair of equations of this form, x equals some function of t, say f of t, y equals g of t, are called parametric equations. Parametric equations are often used to study the motion of object moving in a plane or, in the next calculus course, 3 dimensions. In these applications, t is often time, and then we can think of the ordered pair x comma y, or f of t, g of t, as given the position of an object in the plane at time t. Parametric equations are very, very useful methods of representing curves in the plane or in space. In fact, we'll see that any curve that can be represented by a Cartesian graph, that is a y equals f of x type graph or curve, can easily be represented in parametric equations. The same is true of polar equations, which we'll be studying in the near future. So it turns out that anything you can do for parametric equations can be applied to Cartesian or polar equations. So often these equations are accompanied by an interval from which the t is taken. The variable t in these equations is often called the parameter for the equations, and often t will be restricted to some interval I, which may be a standard closed interval or an infinite interval, anything of that nature. You often think of the I, the interval I, as the domain for the equations. So let's take a look at an example. What can these things look like? So let's start by graphing the parametric equations x equals t squared plus 1, y equals minus 2t minus 3, where t is restricted to be between minus 2 and 3 inclusive. Now there are many ways to graph parametric equations, and one way is this. We can just calculate coordinates xy for several values of t and then plot the points. So in this regard, we might let t take on some values between minus 2 and 3. Here they are. And for a typical value, say like the t equals 2, we would compute the x coordinate as t squared or 2 squared plus 1 to get 5, coming from that part. And the y coordinate is given by then minus 2 times t, which is 2, minus 3, which turns out to be minus 7, and these two values are the ones that occur there. And so with that, we would plot the point 5 minus 7 as one of the points on the curve described by these parametric equations. Let's go ahead and do that. So if we plot the points from this table, we take the various pairs, for example, 5 comma minus 7, and that point appears to be right about here. We do that for every point we plot. And then, as we often do with these things, if we assume that the curve generated is a smooth one, which is generally the case if the equations themselves for x and y are nice and well behaved, then we can draw a smooth curve through these points and declare that to be the graph of these parametric equations. So in this case, we'd see a figure looking something like a parabola. As we'll see shortly, this really is a parabola that opens to the right. Now, a bit more terminology. Often, especially if you're describing motion, when we graph parametric equations, we often think of the motion as starting at the lowest t time, that is time t equals minus 2, and the corresponding point for that, where the object, say, starts if we're describing motion, is called the initial point for the curve. And then when you get to the largest possible value for t, we get to what's called the terminal point for the graph. And as t gets larger, you can see by plotting these points that the point seems to move along the curve in this direction. So again, if you're thinking about motion, these curves often have a direction which kind of shows the direction of the motion along the curve. A second way to produce a graph is this. We can sometimes eliminate the parameter t and actually describe the curve as a Cartesian equation, that is one involving x's and y's. Often the way we can do that is by taking, say, the simpler of the two equations, this linear one, and then solving that equation to get t in terms of x or y. So in this case, that's very easy to do. T is minus y plus 3 over 2. And if we then take that t value and plug it into the x equation in this case, that is the other equation, we find that x is equal to minus y plus 3 over 2 all squared plus 1, which simplifies to this form. And so here we see x depends on y, where y is a quadratic. That implies this relationship describes a parabola. Now the condition that minus 2 less than or equal to t less than or equal to 3 also can be realized. It means that y, in this case, turns out to be between minus 2 minus 3, which is 1, and when t equals 3, the y is minus 9. So y is between minus 9 and 1. And often when we eliminate the t value we see here, we often find we lose information about the initial and terminal points to some degree. Notice t equals 3 correspond to the terminal point, but now it turns out to be the lowest y value, which if all we know is this, it's hard to know which is the initial, which is the terminal point in the curve. Let's take a look at another one. This is a very important example, parametric equations that describe a circle. So here we're going to start with x equals a function of t. X of t is 3 cosine t, and y equals y of t is 3 sine t. We'll let t run from 0 to 2 pi. Again, we can start by plotting some points. So again, we take several t values, as we see here, and for each of those t values, plug the t into the x equation and the y equation to come up with these x coordinates and these y coordinates, the ordered pairs. As before, plot these points. We get a configuration something like that. And if we draw a smooth curve through those points, we see a circle. So this point starts at the initial point with t equals 3, 0. So when t is 0, the initial point for t equals 0, we have coordinate x equals 3, y equals 0. The terminal point, when t equals 2 pi, we see gives us 3, 0 back again. So in this case, the initial point and the terminal point are the same. The curve finishes where it starts. If you track the progress of the points as t increases from 0 to 2 pi, you can see that we're getting motion around the circle like this in the counterclockwise direction. Once again, we can also eliminate the t to obtain a Cartesian equation for this curve. Often when trig functions are involved, it's possible to use trigonometric identities to eliminate the t value and get a relation relating the x and the y. In this case, we're going to note that from x equals 3 cosine t, we can do a very elementary operation and notice that x over 3 is cosine t and y over 3 is sine t. We do that because we have a good trig identity relating cosine and sine. That is cosine squared t plus sine squared t equals 1. So we use that relation down here. And then the cosine squared is the x minus 3 over 2 squared. The sine squared is the y over 3 quantity squared. And this shows us then after a little algebra that x squared plus y squared equals 3 squared. And that's probably a more familiar form for the circle for many of you. Circle of center 0, 0 and radius 3. Now this describes then, as we mentioned, circular motion. In particular, the example we started with here is motion around the circle of radius 3. Circular motion is one of the most important types of motion you'll study in other courses. And you want to realize, too, that this motion can be described by many, many different kinds of parametric equations. In fact, there's infinitely many variations. But for example, we could start with x of t equals 3 cosine 2t and y of t equals 3 sine 2t and let t run from 0 to pi. We'll find that this also describes motion around the circle of center 0, radius 3 in the counterclockwise direction. In a sense, the motion here is twice as fast as the motion was in the original example. and you'll see more about that in later courses. Once again, in this next case, look at the x squared plus y squared sum. It turns out to be 9 again by the usual trig identity. We can let t run from 2 pi to 4 pi. We'll find this also describes counterclockwise motion around the circle of radius 3. In this case, the initial point turns out to be up here on the y-axis at the point 0, 3. And something else, we can also try things of this nature. Notice as long as we have the cosine sine of the same angle, we can use cosine squared plus sine squared equals 1. So once again, this describes motion around a circle of radius 3, and the t parameter to get us once around the circle would look something like this. These are pretty easy to check out, but it just shows the wide variety, the number of different ways you might describe motion around a circle. You can check that each of these equations describes motion around the circle of center 0, radius 3, and check by doing some graphing whether that motion is clockwise or counterclockwise. Sometimes we are given a curve and then want to come up with the parametric equations to describe the curve. Another important example in this case, as well as a circle, is that of lines or line segments. You're going to find parametric equations for the line segment joining the 2 points a equals minus 5, 2 and b equals 5, 12. Set several solutions. First, to illustrate that once you have a Cartesian equation, you can write a parametric equation very easily, we can see the following. It's very easy to check, we'll leave that to the listener, that the line determined by these 2 points a and b has Cartesian equation y equals 1/5 x minus 1. The slope of that segment is minus 5, and when it hits the y-axis, that occurs at the point y equals minus 1 for the y-intercept. Now, once you have Cartesian equations like this, a very easy way to get a set of parametric equations is to simply let the dependent variable, in this case x equals t, and then y equals 1/5 t minus 1. And of course, t, we have to go from the point minus 5, comma minus 2 to the point 15, 2, and so the t value, which really gives us the x, runs between minus 5 and 15. For another solution, again, let's start with the Cartesian expression, y equals 1/5 x minus 1, and let's, for example, let x equal 4t minus 5. And this would be for t between 0 and 5. That, again, is what gets us from minus 5 to 15 in the t range. And then once we have the x value, we can go back to the Cartesian equation and put that in for y. And y becomes 1/5 x minus 1, or 1/5 quantity 4t minus 5 minus 1, which gives us 4/5 t minus 2. So here's another set of parametric equations that describe the line segment AB. And again, in this case, the t range or the t interval is from 0 to 5. For a third solution, we can get even a little fancier, although we don't really gain too much insight. But again, once you let x be anything, we have the Cartesian relation to length of y. So, for example, if we decided we wanted to let x of t equal the log of t, and we'd let t run from e to the minus 5th to e to the 15th, that'll get us the t values between minus 5 and 15. Once again, because y equals 1/5 of x minus 1, we see that if the x is log of t, then y will be 1/5 log of t minus 1. And again, to get us in the necessary interval, t runs from e to the minus 5th to e to the 15. So these examples illustrate that a curve in the plane can often be described parametrically in many, many ways. And sometimes the particular description you want may depend on the physics of the motion or other criterion you may want to consider. So what do we want to remember from this video? Well, first of all, the definition of parametric equations. It's important that you have expressions for x and y that are in terms of some parameter t. and often t will be restricted to a particular interval. The language of this subject, the variable t is called the parameter for the parametric equations, and usually when you graph these x and y coordinates for various values of t, you'll find that the parametric equations describe a curve C in the plane. Okay. And we'll also talk in the future, especially about one of the more important applications, that the x of t, y of t equations often describe the position of an object that's moving. To understand the graph of a set of parametric equations, we can again plot points and then draw a smooth curve to see what the graph looks like. But another nice option is to sometimes eliminate the parameter t, as we did in our first two examples, and then find a Cartesian expression for x and y that describes the graph. Since we're often more comfortable with Cartesian equations, this is often a good way to get more insight into what the graph of a parametric equation might look like. Anyway, also, as we illustrated in example 3, any Cartesian expression y equals f of t can be expressed parametrically by just letting x equals t and then y equals y of t equals f of t. And if x is trapped between a and b in our Cartesian expression, then the parameter t runs from a to b in this expression. Now, to just in conclusion, this is a very important topic. You'll be working a lot with parametric equations when you study motion. Most good calculators have a parametric plotter, so you should make sure your calculator has that function and get some practice with that so you learn how to use the parametric plotter to quickly plot some parametric equations. See you in the next video. Bye.